with the thermodynamics unit. So all these topics will be covered in this particular unit 1, that is thermodynamics. First we'll be discussing about the fundamental ideas, then going on to the continuum model, concept of a system, state, equilibrium, process. Then directly we will be discussing some equations of state. Concept of heat will be discussed in details, first law and second law, and then how these are related to work and entropy terms. Okay. Let us start. First of all, we must know what is system and what is surroundings, how these terms are defined in thermodynamics. So in thermodynamics, the world is basically divided into two parts, system and surroundings. And when you combine both of them, system and surrounding, it's complete. It gives out to be a new term that is the universe. So if I'm observing a beaker which is filled with some hot water, this will be called a system. That is the part which we are actually studying, or system under, or the part which is under observation. That is called a system. The rest other part which is not under consideration, which we are not analyzing, that is called as surroundings. So the part we want to study, such as the reaction, that system, it can be closed, open, or isolated in nature. And if we talk about surroundings, everything else other than system is called as surroundings. And if we combine both of them, that is forming the universe in the thermodynamics. And the line separating system and surrounding, it is termed as the boundary. Okay. These are some basic terms that you must know before jumping on to some detailed topics. Okay. Then here you can see how the system and surroundings can exchange some heat, energy, the mass can be exchanged, some work can be done, and work done by the system, and work can be done on the system and by the system. This boundary isolated, for example, the vacuum flask. This means there is no transfer of energy, no transfer of mass from this particular system to its outside. So a boundary is a closed surface surrounding a system through which energy and mass may enter or leave the system. So depending on the boundary or the membrane which you are taking, so system, energy and mass can change. Okay. And if we talk about surroundings, everything that is interactive with the system is surrounding. And system is a region containing energy and matter that is separated from the surroundings by some, you can say, membranes, walls, or boundaries. Okay. So this is the basic diagram which is showing these things which I told you earlier. So there are basically three types of thermodynamic systems which are there. First is open, closed, and then isolated. As the figures are clearly depicting these things, that open means it is totally open towards the surrounding. System is open towards the surrounding. So mass and energy transfer can occur in both the directions, either from surrounding to system or from system to surrounding. So open systems can exchange both matter and energy with the environment, or you can say with the system. And if we talk about the closed system, they exchange energy. Energy can be exchanged, but yes, it is covered from here with the cork, you can say, in this example. So mass transfer is not possible. And the last is isolated system. Isolated means completely separated from the surroundings. So no mass, no energy, both cannot be exchanged between systems and surroundings. It is completely isolated. Neither energy nor matter can be exchanged with the environment. Okay, so isolated, closed, and open. This can be shown in this way. So these are examples of these systems. As you can see, isolated is shown with the vacuum flask. Okay, matter is not going in or out. Even the energy exchange is not possible. And if we talk about the closed one, if you are keeping something in the pressure cooker, you can say, obviously, like, okay, don't consider pressure cooker, because when the whistle goes up, the mass is also exchanged. So we can consider a container which is covered by a lid. Heat energy will be exchanged with the surrounding until and unless it becomes to the equilibrium state. But matter won't be exchanged because it is covered completely. And if you keep a vessel on the flame, and we are not covering it from the upper side, so it is open. Matter is also getting exchanged from the vapors, energy is also getting exchanged with the surrounding. So these are the examples. Okay, so next consider, okay, let's now quickly come to the concept of heat. What exactly is heat? Okay, heat is actually the transfer of energy across the boundary of a system due to a temperature difference between the systems and surroundings. Energy is getting transferred just because of the temperature difference. That is a heat. It is a form of energy. So when you are heating a substance, it's not like that. Its temperature is rising, but yes, you are transferring some energy into it by placing it in contact with the surroundings, which is having a higher temperature. So transferring the energy. Due to the change in temperature, energy is transferred. And why? For what purpose? To maintain the equilibrium, such that they both attain the same temperature. Temperature difference can be made to zero. So that is why heat transfer occurs when it is a form of energy which is getting transferred due to the temperature differences. Now, don't be confused between heat and temperature term. These are both different. If I define heat, I will define it as flow of thermal energy, whereas temperature is the average kinetic energy. So average kinetic energy means it is associated with the molecules. Average kinetic energy of the system, which is actually associated with the molecules. Okay, taking into together the direction. And flow of thermal energy with temperature difference is actually heat. So measuring device will be also different because these two terms are different. So measuring devices will also be different. So for heat measurement, we use calorimeter, and for temperature measurement, we use thermometer. Again, units for heat is joules or calories, and for temperature, we use degree Celsius, degree Fahrenheit, or Kelvin. We never put degree in front of Kelvin. There's a reason behind that. Because no reference scale, there is no arbitrary reference point for Kelvin scale. So it is not relative, Kelvin scale is not related to any arbitrary reference point such as Celsius and Fahrenheit scale. That is why degree is not there. What happens in Celsius and Fahrenheit? We take a scale, divide into certain degrees, number of degrees, and put each one as 1 degree give value. So no reference, arbitrary reference point is there for Kelvin scale. It's actually a SI unit also, Standard International Unit, which is used by all the industries to mark the temperature um, units on their devices. Okay. So measuring the thermal energy now, we have the expression Q is equal to mc delta T. As I told you, it is just occurring due to the transfer of, due to the differences in temperature. If delta T is 0, then Q equal to 0. No heat transfer. So thermal energy is being measured by using the specific heat. Okay. So phi is the specific heat term, specific heat constant, which varies for every substance. It is depending on nature of material. Okay, C is a specific heat constant, M is the mass, and delta is the final temperature minus initial temperature. Temperature difference. Q is the change in thermal energy. How much energy needs to be transferred? Thermal energy needs to be transferred to maintain the system in equilibrium. That is shown by the Q equal to mc delta T. That's a thermal energy equation. It will be used in various numericals, which I will be showing in the coming slide. Okay. Then effects of heat. There are three phenomena which can occur. I have mentioned two because two are there in the syllabus. But yes, there is one more phenomena, that is the surface expansion. So heat is leading to certain things like expansion. So it is called a thermal expansion. Most materials expand when their temperature increases. It is a normal phenomena which we all have seen in day-to-day lives also. For example, decks of bridges, they need special joint in the ports to allow for expansion. Even a completely filled and tightly capped bottle of water cracks when it's heated. And you can also loosen a metal jar at your home's lid by just running a hot water over it. Okay. So these are examples of thermal expansion which we really apply in our daily lives. So here we'll be studying about linear expansion and volume expansion. Or linear is actually along 1D, volume is along 3D, and surface along 2D. Okay. So before heating or after cooling, we can say the molecules are tightly packed and they are stable. But after heating, what is happening? They are colliding, collisions are occurring, they are moving, they are vibrating. So all these things are happening, and because of this, they are moving apart from each other. That is why expansion is happening, because molecules are getting spread out in the system. Okay. So first of all, we're discussing the average linear expansion coefficient. So when temperature of an object is changed by an amount delta T, its length changes by amount delta L, which is again proportional to delta T and to its initial length L naught. For example, initial length of rod is L naught, and after we increase delta T temperature, delta L expansion was observed in the material. Okay, and delta L, the amount of expansion which has occurred, is actually depending on the change in temperature, and it also depends on its initial length. And when you club both of them, you get it equal to, with some proportionality constant, then L naught delta T. So alpha is the linear expansion coefficient, that is a constant term, which again varies with the nature of material. For example, for steel it will be different, for copper it will be different. So on rearranging these terms, you can get delta L by L naught is equal to alpha delta T. This is the expression which is normally used in the numericals also. Okay. The delta L by L naught change in length upon original length is equal to linear expansion coefficient constant multiplied by the temperature difference. So this is telling you fractional change in length, which is a natural quantity to use, and since we can see different numericals based on this, and then the alpha will be different for different substances. So it's an experimental expansion coefficient which is used to quantify the expansions, and delta T is telling you the change in temperature. Okay, so how temperature changes occur, it has led to the linear expansion. Then similarly comes the volume expansion coefficient. Okay, we will do the volume expansion in the coming lecture. So thank you class. If you have any doubt, you can comment and post it here. Thank you so much. We will continue this part in the next lecture.